Oh, hello guys. Right, I'm talking about exercise 8C and then questions 1, 3 and 5, which are the I'm just getting it up here. This is question 1. This is an example of damped harmonic motion. Okay. Right. So this is my answer to question 1. It's a bit small. See if I can make it bigger. Yeah. Okay. Right. So the particle's moving in a straight line, and we've got the differential equation. This, which defines it. Okay, there's me auxiliary equation, and when I've solved it, I've solved it by completing the square. Okay, and I've got this as a solution here. There's me two solutions. So the complex. So it's e to the minus 2t. I wrote x instead of t because I haven't done it for a while. But e to the minus 2t, a cos 2t plus b sine 2t. There's the 2 for that and the 2 for that. Okay, and then I've worked out the x dt because, oh yeah, we've got the p is at rest. Okay, so yeah, there's that. They've differentiated that. This is a product rule. That's going really little over there. But I've simplified it nice there. Okay, and then subbing in when t is 0, x is 2. So subbing into there, no, that's 1. That's 0. That's 1. So that just leaves a is 2. And then subbing in dx plus dt is 0 because it says it's at rest. So this is 0, 1, 0, 1. So b minus a is 0. So b is 2 as well. And then calculate find x as a function of t. There's x as a function of t. Calculate the value of x if x on t is power 3. Just sub it in and calculate to get x equals 0.09. And then I do a little bit of a graph. I got it a bit wrong. But again, I've got this. You can see it like faintly here. That you've got the exponential decay of the amplitude, and then these frequencies are identical. I tried to do that first, and then fit it in. Okay, so that was question 1. Right, question 3 then was another damped harmonic motion question. Let's just get this up. And on this then, okay, just find x as a function of t. Right, let's do it then. Same again. Solve the auxiliary equation. And when I did that, it's dead dark. This. I'm sorry about that, but when I solved the auxiliary equation again, I got complex roots. So I got this sort of function, which I know straight away that's going to be lightly damped. There's your exponential decay, and there's the oscillation. So, and again, I've not only run out of space, I've cut it off when I took a photo. But there's my product rule there, and it did tidy it up nice. And then the situation is when t is 0, x is 1, and the x dt is 0. So x is 1 leads us to, that's 1, that's 0, that's 1. So a is 1. Okay, when the x dt is 0, that's 1, that's 0, that's 1. So we've got this here is 0. So there's b is root 5 over 5. So there's my expression for x. Okay, I'm going to change colour then because that pen was too fat. So I just made it easier to write with, I suppose. So there's me. I'm just using this expression here for the x plus dt. And having done that then, I'm subbing in t is 0 and the x plus dt is 0. Okay, so I've got it's actually not that hard because we're trying to find when t is p is instantaneously at rest. So that's why the x plus dt is 0. What's nice is that when we do sub that in, this is our expression for the x plus dt, and I feel like of course it is because we get told, don't we, that when t is 0, the x plus dt is 0. So that would mean that it would look like this. There would be no cos term because that would be then non-zero, and that makes sense. So we're after the first time when this is 0. So that is that's never naught. So this has to be naught. Okay, so really, this bit here has to be naught. So obviously, t is naught is one solution, but the other one is t is, well, not t, but this argument here is pi. So root 5t equals pi, so t equals pi over root 5, which is 1.4. Okay, and then let's look at question 5 then. Right, here we go. Get that bigger. Right, okay, so, is that going to move? Yeah. Okay, so there's my little sort of force diagram. And you can see, it's a bit confusing, the minus signs here, but this force is in the opposite direction. Like, so, x is increasing that way. So the force minus 6x is that way, or the force of magnitude 6x is that way. So it's minus 6x. And same with the velocity, it's moving that way. So the resistant force is that way. And that's the reason for this force here being negative, okay? And then there's your F equals mass times acceleration. And rearrange that to get what you want, okay? So part B, then solve it, all right? There's our auxiliary equation. There's the solutions to it. Okay, not very pretty. Okay, so there's your real part, minus half t. There's the imaginary part, there leading to a cos root 11 over 2t plus b sine root 11 over 2t. And then you need to differentiate that. And again, if we're out of space, ridiculous, like every single time we're out of space. But there you go. Okay, and I've tied it up nice again to that. And then using the initial conditions, and these initial conditions aren't that nice. When t is 0, x is 1, dx with dt is positive 2 is 2. So there's my situations there. So t is 0, I'm looking at the x situation here, 1, 0, 1. So yeah, 1 equals a. Nice one. And then dx with dt is 0. No, sorry, dx with dt is 2, well t is 0. So we've got 2 equals 1 times, this is 0, this whole thing is 0, this is 1. So we've got 2 equals this. Okay, and then I just times by 2 and messed around with it to get what b is. So there's my expression anyway for x. So x equals e to the minus a half t times that. Okay, and then part C, find the value of x when t is 2, just sub in on your calculator, get minus 0.459, and it seems reasonable enough, it's right, like. And then, I'm not sure if, I've got like a rectangle hide my graph there, but I'm not sure if you have, but it's again, it's light damping, it's exponential decay on certain terms of the amplitude, it's going like that, well, like that. And then the frequencies are identical as you go along. So it says describe the motion of P for large values at t. Light damping is a good way to say it. Or I've written here as t tends to infinity, x tends to naught. So they're the examples in the book of damped harmonic motion, which is interesting. Next thing we'll look at now, it's just the last few questions in that, is forced harmonic motion, or even forced damped harmonic motion, which really, these are really difficult. And really, I find them really enjoyable, but that's the next thing that we'll do. Nice one.